Swayam Prabha. Digital India. Educated India.
Namaste. In today's tutorial we will discuss how to calculate the eigenvectors and how to check the model orthogonality. So let us go directly into the problem. So here we have to check the model orthogonality of eigenvector. So here K is given to us. The K matrix of 3 by 3 in nature is given to us, and the lambda 1, lambda 2 and lambda 3 value and corresponding omega 1 and time period values are given to us. So by making use of this we will see how to calculate the eigenvector, and then later in second half we will check how to check the model orthogonality of a eigenvector. So first of all, calculation of a eigenvector. Since we have to calculate the eigenvector, it is nothing but the k minus lambda m, mod of k minus lambda m into phi equal to 0 will give us the eigenvector. So if I put lambda 1 as 911.97 in this equation, I will get this phi matrix. Now here phi 1, 1. So 1 indicates the mode number and this suffix indicates the floor level. So phi 11, phi 12 and phi 13. So when I multiply this matrix with this one, which is nothing but the k minus lambda m into phi 11 vector or the 3 by 1 matrix, I will get this 3 equation, first, second and third. So how we get? Let us calculate one equation. So 18.67 multiplied by phi 11 will give me first one, minus 10.36 multiplied by phi 12 plus 0 into phi 13. So since it is 0, there is no need to calculate. So this will give me the first equation. Similarly, second equation will have minus 10.36 into phi 11 plus 18.67 into phi 12, and last term here we have a positive value or some value other than 0, that is minus 10.36 multiplied by phi 13, we will get the second equation. Similarly, third equation. Now here we have 3 equation and 3 unknown, we can easily find out. Now since I want the vector in some normalized form, what I will do is I will assume the top value, which is nothing but the phi 13, as a 1. Now first of all I will substitute this one to get one more unknown value from equation 3. So our equation 3 is nothing but the minus 10 raised to 6 into minus 10.36 alpha 12, which is at the second floor, plus 8.31 phi 13 is equal to 0. So this is third equation. Now if I substitute this phi 13 as a 1, I will get 10.36 phi 12 plus 8.31 is equal to 0. If I compute this one, I will get the phi 12 as 0.802. Now let us see that what exactly physical meaning of alpha 12. Now if I plot this 3 floor, M1, M2, M3. So first of all, for first mode this is the third position or the top floor position, phi 13, assuming it as a 1. So this I will get the first point. Now phi 12 will be over here as a 0.8, 0.802. Now let us see how to calculate or how to get the phi 11. Now in order to calculate phi 11, we already have value of phi 13 as a 1, phi 12 as a 0.802. Now we will substitute this in equation number 2. Now what is equation number 2? Equation number 2 is nothing but the 10 raised to 6 minus 10.36 511 plus 10.67 512 minus 10.36 513 is equal to 0. So this is our equation number 2. Now substituting values, 10.36 511 plus 10.67 into 0.802, which is value of 512, minus 10.36 is equal to 0. So if I solve this one, I will get 511 as a 0.445. So once I plot this 0.445, which is somewhere over here, and I will connect all the dots. So here I will get the values. This will give me the mode shape. So here we got the mode shape of a building. So this is for delta 1, mode shape of a delta 1. Now similarly, so this is our final answer, 0.445, 0.802, 1. We are writing from first floor to third floor or the topmost floor. If I draw the diagram, 513, 512 and 511. Here we have 513 as a 1 and 0.802 and 0.445. Now similarly we can calculate the mode shape, that is a 5 vector for second mode, by substituting lambda 2 as actual value of 7159.72. So by substituting lambda 2, I will get this 2 matrix, and again multiplying this 2 matrix with each other, I will get equation number 1, equation number 2, equation number 3, again with the 3 unknown of 521, 522 and 523. The way we have assumed the value of 513, here also we will assume value of 523 as a 1. Now rewriting the equation number 3, 10.36 522 minus 5.75 523 is equal to 0. So this is my equation number 3. Now 10.36 522, which is unknown, 5.75 1 multiplied by 1 is equal to 0. So 522 is equal to minus 0.555. So here you can observe that though value is less than 1, but it is having the negative sign. Similarly, let us write the equation number 2, which is nothing but the 10.36 521 plus 4.61 522 minus 10.36 523, this is the entire bracket, is equal to 0. So now I will substitute each and every value one by one. 4.61 multiplied by minus 0.555 minus 10.36 into 1 is equal to 0. So I got 521 as 1.247. So again negative value but greater than 1. So when I plot this one, you can see that I will get 1 on the rooftop as a 5 2 3, and then second one at the second floor, which is 5 2 2. Because of negative sign, it is on the left hand side, 0.55, and then third value at the first floor, which is highest. If we just look at the absolute magnitude as a 1.247, but since it is negative, we are drawing it on the left hand side as 5 to 1. So this was the second mode. Now the same way, when we go for the third calculation, we get the 2 matrix. This 2 matrix multiplication of this 2 matrix will lead us to a 3 equation where we have 3 unknowns. This time, for when we assume alpha 3 3 as a 1 and rewriting the third equation 10 raised to 6 minus 10.36 532 minus 23.28 533 is equal to 0. This was my third equation. When I substitute again 10.36 532 is equal to 23.28 multiply by 1. So here I will get 532 as minus 2.247. So this is a value at the second floor. Now when I substitute for first floor in equation number 2, minus 10.36 531 minus 12.92 532 minus 10.36 533 is equal to 0. So this one is second one. Minus 10.36 531 minus 12.92 multiply by 532 value as minus 2.247 minus 10.36 is equal to 0. 531 is equal to 1.802. So here we also got the values of phi for third mode in first and the second floor. Now when I plot this one, I will get on the this kind of vector and this kind of diagram. So this was the lambda 1, lambda 2, lambda 3 value, corresponding omega values and the corresponding time period. And this is the eigenvector which was for lambda 1, lambda 2 and lambda 3. So this is the phi matrix. So this can be called as a vector, and entire matrix we can say as a phi matrix. So this is the physical meaning of it. So for lambda 1, phi vector consists of phi 13, phi 12, phi 11 with corresponding values. The magnitude will give us from center of mass of that floor, how much far it is from center of mass of that floor, and the positive and negative sign will give us about the in which direction it is, and when we draw it we will get the mode shape. So these are the mode shape for third one. So here we can see that for the first mode it will touch the vertical axis only at a one point. For second mode it is touching at the first point and at second point, and for third mode we are touching vertical axis at the bottom, at the middle one and the third one. So this can be a cross check for the calculation of a phi values. Now let us see how to check the orthogonality of a eigenvector. Now when we see when we have to define the model orthogonality of a matrix, we have to prove that phi transpose k phi should be diagonal matrix. What is a diagonal matrix? Diagonal matrix means we only have diagonal element as a some value, non-zero values, rest all values are 0. So if we can prove this, we can say that the phi matrix is orthogonal. So here now I am substituting this is the phi matrix which we have just now calculated, and this one is a phi transpose and this is a k matrix. So when I multiply this phi transpose k and k into phi, ultimately I will get the answer as this matrix. So this has a diagonal element as a non-zero value and all non-diagonal element as a 0. By this we can prove that the modal orthogonality exists. Till now we have checked the manual method to find out or to check the modal orthogonality, where we have computed the phi transpose k phi. So product of phi transpose k phi gave us the diagonal element or the diagonal matrix. So that is a one part or the one way to prove that the modal orthogonality. Now we will see how to check the or the prove modal orthogonality for graphically or the graphical method. Now here we have 5 matrix which we have already calculated, every one of you know. Now when I suppose these are the 3 axes, this is x, this is y, this is z. Now you can consider this row as a x, this row as a y, this row as a z. Now let me plot a single point. So each vector will give me one single point. Let's say alpha 1. Now I will first of all I will plot this alpha 1 1 in a graph or in a space, and then I will connect it from the origin. Origin is nothing but the 0 0 0. Now let us say x value for phi 1. So phi 1 in x direction is around 0.45. Say this is 0.445. Then in y direction it is 0.8, which is somewhere around here, 0.8. And then in z direction it is 1. I have to find out that in space. So this was x direction, here it was y direction. Now if I go vertically, z direction up to 1. So I got this point as phi 1. Now if I connect it through origin till that point, I will get this vector. From origin it is going outward. Now when I compute the same thing, same point for phi 2 and phi 3, let us look graphically how it will look. Now here you can see these are the 3 vector. The way we have generated phi 1, I am plotting phi 2 and phi 3. So when I plot this in any plotting software available, you can see that from origin how they are going and how they are orthogonal to each other. They are perpendicular to each other and they will not cross each other in the space. So if we can prove this, or if you can draw this, this is also one of the method to check the modal orthogonality.